Hello, class. Today we are going to use the ideal gas law to calculate quantities of pressure, volume, temperature, and moles of a gas. We'll also be able to find the molar mass of a gas in a sample. The ideal gas law is derivative of the combined gas law and the other simple gas law relationships that we have studied previously. In the ideal gas law, we are always going to be given at least three of the variables that we need, and we can solve for the fourth. When I say variables, I'm talking pressure, volume, temperature, and moles of gas. In the equation, PV equals nRT, we also have something called the universal gas constant. This allows everything to stay proportional to each other, and it serves as a reference point to STP, which is standard temperature and pressure. Essentially, it allows all of the units to cancel out when we do the math. So for that reason, the units for R depend on the units of P, V, T, and N. The gas constant that we're going to use has units of atmospheres for pressure, liters for volume, Kelvin for temperature, and MOL, moles, for moles. The letter N is used to represent moles in this case. They didn't use the letter M because it already was in use for mass. So N is moles. So just keep in mind, like I said, the units for R, atmospheres times liters divided by moles times Kelvin. So you're going to see this a lot. This is the units for the R gas constant. As I mentioned before, we can find the R gas constant by using the volume of 1 mole of gas at standard temperature and pressure. Remember, standard temperature and pressure is 0 degrees Celsius or 273 Kelvin, and standard pressure is 1 atmosphere. It has been determined that the volume of 1 mole of gas is equal to 22.4 liters at that temperature and pressure. So first, we need to rearrange our equation so that way we can solve for R. So to get R by itself, I need to divide both sides of the equation by N and T. On the right side, N cancels and T cancels, so we end up with PV over NT. So let's take these quantities of 22.4 liters, 1 mole, 273 Kelvin, and 1 atmosphere, and we'll plug those in. Oops. So we had P times V over N times T. Now we are going to multiply those things together. When we solve the equation this way, we need to pay attention to order of operations. So we're going to multiply the two things on top, multiply the two things together on the bottom, and then we'll divide top by the bottom. All right, so 1 atmosphere, so I use parentheses, 1 atmosphere times 22.4 liters divided by, open parentheses, 1 mole times 273, and I close parentheses. This gives us a value of 0.08205, and none of the units canceled out, so this has units of atmospheres, liters, mole, and Kelvin. This whole number is one giant combo unit. Now, we tend to use 3 significant figures, so for the purpose of what we're doing, we're going to round this to 0.0821. You don't need to memorize that. It is going to be given to you in the problem set, but that's what we're referring to when we're referring to as R. So let's go ahead and solve a couple of problems together. There's some useful information at the top. We obviously have the ideal gas law, which is PV equals nRT. We have some conversion factors that we talked about in the last lesson for our pressure units. We have millimeters of mercury, torr, kilopascals, and atmospheres. We have a reminder that STP is 1 atmosphere and 273 Kelvin, and at STP, 1 mole of gas is equal to 22.4 liters. We have our Kelvin and Celsius conversion equation, and then we also know 1,000 milliliters is 1 liter. Yes, you will have to do some conversions here. So in this first problem, it says what pressure will be exerted by 0.3 moles of gas contained in an 8-liter vessel at 18 degrees Celsius. So before I can solve, I am going to need to make sure all my numbers are in the units that match with my R gas constant. I've got moles, I've got liters, I'm going to solve for atmospheres, but my temperature is in Celsius, so I need to convert to Kelvin. Oops, 273 plus 18. 291 Kelvin is the value that we're going to plug in for our temperature. This first problem is asking for pressure. We're going to solve for pressure. So we're going to take our ideal gas law and the value that we want is P. So to get P by itself, I need to divide both sides of the equation by V. In doing this, V cancels out on the left side, and I end up with this new equation, nRT over V. So I'm going to plug my numbers in. So I've got 0.3 mole times 0.0821, and I'm going to write the units atmosphere, liter, mole, and Kelvin, and then my new temperature of 291 K. And then I'm going to close parentheses because all three of those things get multiplied together in the calculator first, and then we're going to divide by our volume on the bottom, which is 8 liters. So 0.3 times 0.0821 times 291 divided by, and notice I closed parentheses after that, divided by 8 liters. I get that my pressure is equal to 0.89, and I'll round to the third decimal place. 0.896. Now let's double check our units. Because we multiplied moles and Kelvin by the gas constant, moles cancels, Kelvin cancels, and then we did liters divided by liters. So the only unit that's left over is atmospheres. So this is 0.896 atmospheres, or ATM. So using the same setup, go ahead and solve questions 2 and 3. Pause the video now. Welcome back. Here we are. Same setup, nRT over V. You did have to convert temperature into Kelvin for number 2, and it has the exact same setup. Moles times R times the temperature divided by 2 liters. We would have gotten an answer of 67.5 atmospheres. For the third problem, you had to convert milliliters into liters and then put that in your denominator. So make sure you convert first. It's very important so that the units end up in the correct place. On to number 2. This time we're going to solve for volume. You probably guessed it, this is going to be a very similar setup to last time. We have our gas law, PV equals nRT, and I see that I'm solving for volume this time, so both sides need to be divided by the pressure, so that pressure cancels out on the same side as volume. Now my equation is going to be nRT over P. Before I can plug anything in, I need to check my units. I see 880 torr, which should be in atmospheres, so I'm going to have to convert that. Remember, and I'll do it down here in a visible color, 880 torr is very similar to millimeters of mercury. So 760 torr on the bottom, 1 atmosphere on top. This is the same thing as dividing, so we can multiply times 1 over 760, and you'll get your answer, or you can just jump to 880 divided by 760, and you get the same answer. So my pressure, if I convert this properly, is going to be 1.1, let's say 1.16 atmospheres. I also need to convert my temperature, 35 plus 273, and that's going to be 308 Kelvin. And then moles is good to go, and I have my gas constant. So now I can plug in my numbers. So I've got 0.77 mole times 0.0821 atmospheres, liters, moles, and Kelvin times 308 K. Same deal. I multiply all three of those numbers together first, then I divide by my pressure of 1.16 atmosphere. And I can check my units. Moles is going to go, Kelvin's going to go, atmosphere is going to go. My final answer should be a volume in liters. So 0.77 times 0.0821 times 308. And then I'm going to divide that by 1.16 atmospheres. So this is a pretty large container, 16.79 liters. 16.79 liters is my volume of my gas. Go ahead and calculate and solve for problems 5 and 6. Pause the video now. Welcome back. Here we are. A couple of tricky things happened here. The first one, we had to convert our pressure into atmospheres. Same setup as the problem before. We got an answer of about 14.3 liters. Number 6 might have been tricky for you. It tells us we're at STP. So you have to look at that useful information box at the top. And we know at STP, we're at 273 Kelvin and 1 atmosphere. So yes, they did give you a temperature and pressure by telling you STP. So if you used method number 2, I have 2 methods here. Method number 2 we'll cover first is how we have solved the other 2 problems. So moles times R times T over P, and we get a volume of 18.6 liters. There's a second way we can solve this. When things are at STP, standard temperature and pressure, we know that 1 mole is equal to 22.4 liters. That is a conversion factor. We could have just done some stoichiometry and said 0.83 times 22.4 liters over 1 mole, and we got the exact same answer. Now, yes, the first method does require less work, but you can only use that when we're at STP. If we're at any other temperature or pressure, it does not work. All right, this time we're going to solve for temperature. So let's take a look at our equation. PV equals nRT. I see temperature by itself, so I want to divide both sides of the equation by the neighbor, nR. So that way we can get rid of n and r on the right side. And we're left with T. T is going to be equal to PV over nR. Order of operations, we're going to have to multiply pressure and volume together first, and then divide by moles times the gas constant. But make sure you multiply moles and the gas constant first. All right, let's check out our values and see what we need to convert. We need to convert 645 torr to atmospheres. So we have 0.84, we'll say 849 atmospheres for that. We also have 400 ml that needs to go to liters. If you divide that by 1,000, we get 0.400 liters. And then we've got moles. Everything else is good. Notice that our answer will be given to us in Kelvin, so we won't need to do any extra temperature conversions here. So let's go ahead and plug in. We've got, 0.0849 atmospheres. I'm going to open parentheses times my volume, which is 0.4 liters, close parentheses, and then I'm going to have my moles, 1.35 moles, times my gas constant, 0.0821 atm liter mole Kelvin. That is a K there, I apologize. If we check our units, atmospheres is gone, liters is gone, moles is gone, and we'll be left in Kelvin for our final answer. All right, order of operations, open parentheses, 0.849 times 0.4, close parentheses, divided by open parentheses, 1.35 times 0.0821, close parentheses. Guys, remember those parentheses are going to be really important for the order of operations. You will be getting incorrect answers if you do not use the parentheses correctly here. Order of operations, multiplication first, then division second, right? PEMDAS, P-E-M-D-A-S, multiplication before division. All right, and we get our temperature here of 3.06. Really is just we could say 3.1 K. Now that's a very, very low Kelvin temperature. I just made up some random numbers, so I apologize. That is a very, very low temperature. That's almost at absolute zero. Very, very cold, but the method still works, okay? Go ahead and try 8 and 9 on your own. Pause the video now. Okay, welcome back. Here we are. Number 8 gave us a pretty realistic temperature, 181 Kelvin. That's negative 92 degrees Celsius, in case you're curious there. But we had to convert our pressure into atmospheres and then plug in PV over NT, use order of, or not NT, sorry, PV over NR, and then use our order of operations, okay? Number 9, you had to convert kPa to atmospheres. Hopefully you remembered to use dimensional analysis there, or just divide by 101.3 kPa. And then we can plug in and solve. Again, we get a really low temperature for this particular problem, almost at absolute zero. All right, almost through the 4 different variables. This time we're going to solve for moles. This is the last variable we have to solve for. So PV equals nRT. This time I want N, so I'm going to divide both sides by R and T. So that way R cancels, T cancels, and I'm left with PV over RT. Same order of operations issues we're going to have to work out here. So we're going to have to multiply the 2 numbers on the top, multiply the 2 numbers on the bottom, and then divide by each other. All right, let's convert our numbers to appropriate units. 750 milliliters is going to be 0.750 liters. 15 degrees Celsius is going to be 288 Kelvin. And then 975 torr is going to be 1.28 atmospheres. Okay? And we want to know how many moles of gas we've got. So 1.28 atmospheres times 0.750 liters divided by our temperature times our gas constant. ATM, liters, moles, and Kelvin. And then if we check our units, I see that atmospheres is gone, liters is gone, moles is not gone, sorry. Kelvin is gone. I'll be left in moles in my final answers here. All right, so order of operations, multiply the 2 on the top, close parentheses, multiply the 2 on the bottom, in parentheses, and then do top divided by bottom. and I get 0.0406 moles of gas. Okay, go ahead and try 11 and 12 on your own. Pause the video now. All right, welcome back. Check your answers real quick. You did have to convert kPa to atmospheres for number 11 and also get that Kelvin temperature. Number 12, millimeters of mercury, had to go to atmospheres. And then we can get our answers. All right, saving the best for last. The last kind of problem is determining molar mass of a gas using the ideal gas law. Guess what? Like we said before, we're going to use the ideal gas law to solve for moles, which is what we just did. So this is really just an extension of part 4. We're adding one more step to it. So we already know N is going to be equal to PV over RT. So we can go ahead and get set up for that question. There's a lot of information here. There is a pressure value, a temperature value, a volume, and then a grams. Ooh, okay, we're gonna have to see where that goes in a little bit. Let's use what we know how to use. First, our 755 millimeters of mercury is gonna have to go to atmospheres. 755, 0.993 atmospheres. Okay. My temperature is already in Kelvin and my volume is already in liters. Wow, this is a nice problem. Okay. So then we're going to go 750, oops, sorry, not 755, I already converted. 0.993 atmospheres times 18.94 liters. And then on the bottom, I've got 270 Kelvin times 0.0821 atmospheres, liters, moles, and Kelvin. All right, I'm going to go through and get my moles here. Oops, I forgot parentheses. Parentheses, 0.993 times 18.94, close parentheses, divided by 270 times 0.0821. All right, I get 0.848 moles of gas. All right, but that's only part of my answer. I need to figure out the molar mass. Remember what I said before, molar mass has units of grams per mole, or grams divided by moles. So we're going to take that grams they gave us in this problem, 60.18 grams, and we're going to divide it by what we just got, 0.848 moles. And when we do that, we're going to get the molar mass of our gas. Now, this is important because it could throw off your answers. I'm going to use the second answer button. Oops, second answer. That's going to take my previous answer, the complete thing. I'm not going to truncate and put in only 0.848. I'm not going to have any rounding errors. I'm just going to put the whole thing in. And this gave me an answer of 70.92 or 93 if we round. 70.9 grams per mole is the molar mass of my gas. This is going to be my final answer. So it asks for molar mass, we have to do grams over moles, and then it says identify the gas when finished. How can we do that? Well, at the end of your worksheet, I have a nice little reference table here. So we're going to try and find the one closest in mass to what we just calculated. 70.929 or 93 is what we got. This is the closest molar mass. This must be chlorine gas. So the identity of this gas is Cl2. Go ahead and try numbers 14 and 15. Use that reference table to identify the gases. Pause the video now. All right, welcome back. This is the last problem we have to check. So here we are. All right. In number 14, we did not have to do any conversions, but we did have to do our grams divided by our moles, and we got a molar mass of around 48 grams per mole, and that should have been O3. Number 15 was a little bit meaner. You had to do conversions for all three values. Pressure had to go to atmospheres, temperature had to go to Kelvin, and volume had to go to liters. Then once you solved for moles, 0.527 grams divided by that mole value that you calculated, you should have gotten 17.01 grams per mole, which is ammonia, NH3. Okay, that is all for this video lesson. That was a lot of algebra. Go ahead and try part 6, which is a mix of all of these problem types. See you in the next one.